Assalamualaikum dear students, I hope you all are fine and in the best conditions of your health. So in today's lecture, we shall discuss about introduction to aromatic hydrocarbons. So the key concepts which we shall discuss in this lecture is the discovery of benzene. I also consider about the nomenclature of substituted benzene, and we shall also see about stability and the structure of benzene. So starting from the discovery of benzene. So in the early 19th century, the oils that was used to light the streets of London and other cities in Europe, so this oil came from whale fat, right? So a scientist named Michael Faraday was interested to know what is the composition of this whale fat. So in order to determine the composition of this whale fat, what he did, he heated this whale fat to obtain a colorless oil, right? And this colorless oil, when determined, it had empirical formula of CH. So this empirical formula of CH, it posed a very surprise among all of the scientists, because an organic compound having such simple formula, empirical formula, so it started a debate that how can we justify the four valencies of carbon if a compound have an empirical formula of CH, right? So this surprisingly simple empirical formula with just one carbon and one hydrogen, that was quite a surprise. And at that time, determination of structure for such a compound was a challenge. Another important aspect of this structure is that the structure was unusually stable. It was very stable and it was chemically inert. So this compound does not react with different reagent under ordinary conditions, right? So this surprisingly simple empirical formula and this external stability along with this chemical inertness, this made this molecule a compound of very much interest. So this molecule was named as benzene, and later studies showed that the molecular formula for benzene is C6H6, right? So in the previous slide we saw that the empirical formula for benzene is CH. The empirical formula shows the simplest ratio between the atoms, while the molecular formula gives you the exact number of atoms in a molecule, right? So benzene has a molecular formula of C6H6, means each carbon is attached with one hydrogen. So the ratio of carbon and hydrogen is 1:1. So benzene has 4 degrees of unsaturation. So what do you mean by 4 degrees of unsaturation? The unsaturation indicates how many hydrogens are deficient from a molecule. So if a molecule has all single bonds, then molecules have to be saturated, but in case if there is a double bond or a triple bond, we say molecules are unsaturated, right? But in case if you remember the cycloalkanes, we mentioned that in cycloalkanes, when we convert a open chain system into a ring, we have to remove 2 hydrogens from each end, right? So 2 hydrogens are lost when we close a ring system. So benzene has a ring system. It means it has 1 degree of unsaturation because of the ring, and it has 3 double bonds, right? So each double bond has 1 degree of unsaturation. So in total, benzene has 4 degrees of unsaturation because benzene has a ring and it has 3 double bonds. So yeah. So apparently the structure of the benzene is structure of cyclohexatriene, right? So this 6-membered ring, so this cyclohexa, and because of presence of 3 double bonds, so the structure is just like the structure 135 cyclohexatriene, right? So according to Kekulé-Loschmidt, this benzene resembles 135 cyclohexatriene. However, another surprise is that benzene does not exhibit any kind of reactivity which is similar to a conjugated triene, right? So benzene is extremely stable while the cyclohexatriene is not stable at all, and it is comparatively unreactive as well, right? So benzene is not completely unreactive, it's comparatively unreactive, right? it does react under some conditions, but you need to have a catalyst for benzene to react, right? So if you are reacting benzene in absence of any catalyst, then in that case benzene will not react at all. But in case if you are using some catalyst such as some alloy acid, then in that case benzene will react, right? And when benzene reacts, it does not give addition product, right? So you can see here that this is a benzene and we are highlighting a double bond here, right? So we want to react the benzene and we are focusing on this double bond. So if in case if benzene is just like cyclohexatriene, then addition of bromine through this double bond will take place, right? So if bromine adds to this double bond, the product should be this one, right? But in actual, what happens when we react benzene with this bromine in presence of a catalyst such as ferric bromide, we don't get this product. Instead we get substitution product, right? So double bond remains at its position. Instead what happens that this hydrogen has been replaced by this bromine. So it means that benzene is not acting just like a simple cyclohexatriene, but it is behaving somewhat differently, right? So although benzene has 3 double bonds, but it forms mono-substituted product, right? So according to Kekulé, benzene consists of 2 forms that are in equilibrium with each other, right? So just remember that when we say 2 things are in equilibrium with each other, it means that both of these forms are real, right? So in case if Kekulé was right, then if we carry out the bromination of monobromobenzene, then we'll get the isomer in which both bromines will be attached to a double bond like this one, and we will get another isomer in which the bromines are attached an adjacent carbon which are separated by a single bond here, right? So you can see 2 bromines which are attached to a double bond and 2 bromines which are attached through a single bond. But when we carry out the bromination of this monobromobenzene, we get only one product, and the experimental evidence show that both of these are same, right? That's again a surprise, right? So now we know that this idea of Kekulé that benzene is actually in equilibrium with 2 of its forms, this idea is not correct. So now we know that benzene is a conjugated cyclic system, and since the system is conjugated, then it has the delocalization of the pi electrons, and this delocalization of the pi electrons gives benzene some extra instability. Also from the previous lecture we know that whenever there is conjugation, there is delocalization, and whenever there is delocalization, we cannot write a single formula for a compound. So we have to make use of more than one structure in order to explain structure of an original molecule, right? So benzene is represented by its different resonance forms. Also, it has been studied so far that in benzene all carbon-carbon bonds are equivalent, they are same. So there is no pure single bond or pure double bond in benzene. So all the bonds of carbon-carbon in benzene, all of them have the same bond length. Also the bond angles in benzene are same in all cases, right? So now let's consider the nomenclature for benzene, right? So far we have considered that benzene is different. So it was historically discovered when the whale fat was heated, and the empirical formula that was quite simple that surprised the scientist and explored towards and promoted to explore the structure of such a surprising molecule. Also, although apparently benzene is a cyclohexatriene system, but benzene does not show the reaction of double bond. Instead, it shows substitution reaction instead of addition reactions, right? So now we are considering the nomenclature of substituted benzene. So previously, benzene and its derivatives, they were called aromatic compounds because most of them have strong smell, right? This, the word for smell is aroma. So most of the benzene and its derivatives, they have strong aroma. So that's why they were known as aromatic compounds. Although the smell of benzene is not pleasant, it's not fine, it's very irritating, but still it's considered as the parent aromatic compounds because most of the aromatic compounds, they are derived from benzene, right? So another thing that you should keep in mind when you are considering this benzene systems, that whenever you see a benzene ring with 3 double bonds like here, just remember that it is one of the contributing structure of the benzene, so it's not a real structure. So this is not real structure, this is not real structure, they are contributing structures and they are explaining a structure which cannot be drawn on paper. So alternatively, what we can do, we can draw a 6-membered ring and we can put a circle inside. So putting a circle inside the ring is a means to show that all of the carbons have equal electronic density because of delocalization of pi electrons here. So again, nomenclature. So if you have a mono-substituted benzene, then the IUPAC nomenclature for such a system is that the substituent is written as a prefix to benzene, right? So benzene will be written in the end and the substituent will be attached as prefix here. So here we have a fluorine, so the name for this structure will be fluorobenzene. Similarly, we have nitrobenzene. Now here in this case, we have a side chain which is attached to the benzene, and this side chain is further substituted, right? So if you have a substituent to a substituent, right, the basic substituent is this carbon and this carbon is further substituted. So whenever you have a substituent to substituent, then you have to write the substituent in small brackets, right? So how we'll write? So we'll consider longest continuous chain. Suppose this is longest continuous chain, right? So this is 2 carbons, so this is ethyl, and you can see that on this carbon we have 2 substituents which are methyl here. So this carbon which is directly attached to the main group, so this carbon will be numbered as 1, right? So this side chain will be named as 1,1-dimethyl ethyl, right? So the main group is this ethyl group, and to this first carbon of the ethyl we have 2 methyl groups, right? So in small brackets we will write 1,1-dimethyl ethyl, and in the end we will write benzene. So the common name for this structure is tertiary butyl benzene, but the IUPAC name will be 1,1-dimethyl ethyl benzene, right? So this is the system in case if you are having monosubstituted benzene. So in case if you have disubstituted benzene, then the relative positions of the substituents is represented in different manner. So in case if the 2 substituents are on adjacent carbons, like this one, so this chlorine and chlorine, this is on adjacent carbon, we say the substituents are having 1-2 relationship because one is on carbon 1 and another is on carbon 2, and these substituents are said to be ortho to each other. So we say these 2 chlorines are ortho to each other, and ortho is represented by italic O. So whenever you see a small o which is written in italics, you can see that 2 substituents which are being mentioned, they are ortho to each other. That means they are having 1-2 relationship. Then in case if the 2 substituents are at 1-3 position, so one is at carbon 1 and other is 2-3, so other is at carbon number 3, then we say the substituents are having 1-3 relationship and the substituent are said to be meta to each other. So meta is represented as small m, which is written in italic. Alright, so the name for the structure will be 1-bromo-3-nitrobenzene. Just remember that the substituents are written in the alphabetic order. So B comes first, N comes later. So therefore bromo will be written first and nitro will be written later. So here we have another group. So here you can see we have an ethyl group, and here we have an isopropyl group, right? So in case you're to write this group here, then again the system will be select longest continuous chain. So we have a continuous chain here, and this is a substituent, and this methyl is attached to the carbon number 1, right? This carbon will be number 1 because it's directly attached to the benzene ring. So this group will be named as 1-methyl ethyl, right? So again we have a substituent of a substituent, therefore we'll write it in the small bracket, right? So we have a methyl ethyl group and an ethyl group. So E comes first, methyl ethyl comes later, therefore this will be 1-ethyl 4 1-methyl ethyl benzene. Right, so this is relationship. You can see these are at 1,4 relationship, so they are para to each other. Right, so you can also see, you can also write as para ethyl isopropyl benzene, but this is a common name, right? So IUPAC name is 1-ethyl for 1-methyl ethyl benzene. Now, if you have a dry substituted benzene or more highly substituted benzene, then the simplest rule is that the numbering of the ring should be done in such a way that all of the substituents get the lowest number. Right? So for example, here you can see we have 3 substituents, so we can start the numbering from 1, 2, 3, 4, 5. So in this case, one substituent is getting 1 number and the other is getting 5 number. But if we number from 1 to 3, all of the substituents are getting lowest number. So whenever you are naming a benzene ring that is highly substituted, then in that case always remember that you have to number in such a way that all of the substituents get the least number. Right? So here the structure will be known as 1-bromo 2,3-dimethyl benzene. Alright, so again the substituents will be written in alphabetic order, and since it becomes first, so we are assigning it to 1 carbon and then 2 and then 3. So next is here system, so we can number it 1, 2, 3, or we can number 1, 3, 4, 5, right? So in case 1, 2, 3, so in case if we are starting number from here, the first substituent is carbon number 1 and other is on carbon number 3. But in case if it number like this one, 1, 2, 4, then in that case we are getting 2 substituents at a lower number. Right, so prefer numbering from this side instead of numbering from this side. Also we'll not numbering from this side because the substituents will be assigned higher number. So we are trying, whenever we are to number, we have to name a benzene ring, so always ensure that all of the substituents get the least number. Here we have 3 substituents, so one substituent is ethyl, one is ethenyl, and other is ethynyl. So now again we can number it from here or we can number it from here, but in the alphabetic order you can see that first 3 alphabets are the same in ethyl, ethenyl or ethynyl, so we have to see the 4th point of difference. So in case of ethenyl, the 4th alphabet is E, while in ethyl it's Y, and in ethenyl it's also Y. So firstly we will write 1-ethenyl because it's alphabetically coming first. Then we have ethyl and ethenyl, so we have to distinguish which will come first and which will come later. So you can see that both have 4th letter Y, but the 5th letter is different. So in case of ethyl we have L, and in case of the ethenyl we have N. So since L comes first, therefore the second substituent that will be written will be ethyl. So this name for this compound will be 1-ethenyl, 3-ethyl, and 5-ethenyl benzene. Right? So just remember that you have to follow the sequence for alphabetic order here. Right, so in case if you are having substituents on the ring, so we can use the prefixes of ortho, meta, and para. So just remember that the substituents which is of highest priority is placed at carbon 1. Since this carbon 1 to which the highest priority group is attached, this carbon is known as ipso carbon. So here we have 2 substituents, one is iodine and other is methyl. So the iodine is having higher preference, therefore the carbon that is having iodine will be number 1 and methyl will be considered as number 2. So they are having ortho relationship because they are at carbon 1 and carbon 2. So this carbon that is having iodine, this will be ipso carbon and it will be numbered as 1. So here we have 3 bromine and 1 hydroxyl. So hydroxyl has a higher preference. So since hydroxyl has higher preference, so this carbon to which hydroxyl is attached, it will be numbered as 1. So this is ipso carbon, and you can see relationships. So this hydroxyl and bromine, this is ortho because they are 1 to each other. Similarly, this hydroxyl and this bromine, they are 1 to each other, so they are also ortho. this hydroxyl and this bromine, so they are at 1, 2, 3, 4. They are 1-4 relationship, so they are parallel to each other. And these bromines are having 1-3 relationship, so they are meta to each other. You should know about the terms of ortho, meta, and para. And also you should know what's ipso carbon. So ipso carbon is a carbon to which the group of highest priority is attached. So we assign one number to the ipso carbon. Right? So it's also important that since we mentioned that previously aromatic compounds were called aromatic compounds because they had very strong aroma, they had very strong smell. So most of the compounds that were discovered earlier because of their fragrance, so most of these compounds are known by their common names, and these common names are also accepted by IUPAC. For example, here we are seeing an organic compound. The common name for this organic compound is methyl salicylate, right? So this compound has a common name of methyl salicylate, although it has its own IUPAC name of methyl 2-hydroxybenzoate, but this methyl salicylate is also accepted as IUPAC name. Similarly, this structure has a common name of vanillin. So the vanilla flavor you used in different foods, so this vanilla flavor has structure of this compound. So although it has also a IUPAC name of itself, but the common name of vanillin is acceptable by IUPAC, right? So there are a number of compounds for which the common names are acceptable as IUPAC name as well. However, it's always better to use the IUPAC name instead of preferring the common names. So now we are having another 3 terms: the arenes, aryl, and phenyl, right? So what is the difference between these 3 terms? What's an arene, what is phenyl, and what is benzyl? So in general, if a benzene is substituted, it's called arene, right? So whenever, whatever be the substituent, right? So whenever benzene is substituted, then the substituted benzene is known as arene, right? In case if in a compound benzene is a substituent, right? So if benzene is used as a substituent in any compound, then such an arene is called aryl group, right? So this is general description. So whenever benzene is substituted, then it's called arene. If benzene is acting as a substituent, then it will be called aryl group and is represented by Ar. But in case if a substituent is attached to the benzene ring, right, then the benzene is called phenyl and is represented by PH, right? So now in case if a phenyl group, so you can say phenyl group is attached with a CH2 group, right? So this fragment in which this phenyl group is attached to CH2, this group is known as phenyl methyl, or it's known as benzyl group. Right, so you should know about the terms of what's arene, what's aryl, what's phenyl, and what's benzyl. So if benzene is acting as a substituent, it's aryl. If a substituent is attached to benzene, it's phenyl. If a benzene is attached to a CH2, then it's called benzyl. And in general, all of the substituted benzenes are called the arenes. Right? Now let's consider the structure and resonance stability of the benzene. So benzene is unusually unreactive. It doesn't react with common reagents at room temperature, for example. It doesn't react just like double bond or conjugated alkenes. It doesn't react with acids, doesn't react with hydrogen, bromine, or cheminophore. So in case if you have to react benzene with these conditions, either you have to make use of a catalyst or you have to give very harsh conditions. So why benzene is not reactive? The reason for this poor reactivity is the delocalization of the pi electron. In case of the double bond, if you have a simple double bond, the electronic density is available for attack on any electrophile. But in case of the benzene ring, these electrons of the pi system, they are not just pi electrons, they are forming a ring current, right? So this ring current which is forming on the benzene ring, so this is circulating on the ring, it's not available at only single one point. So because of this delocalization, the benzene ring is extraordinary stability and it is very less reactive. So the stability of the benzene ring is expressed in terms of resonance energy. So we say that because since benzene has very large resonance energy, therefore it is very stable, right? So in order to consider the stability of the benzene, let's estimate resonance energy by comparing the heat of hydrogenation of 1,3-cyclohexadiene and some related molecule. So let's consider firstly that if benzene were actually cyclohexatriene, right? Just for the time being, we are imagining that if benzene is a conjugated cyclohexadiene system, right? So in case if this was the case, then we must have some alternation of single and double bonds in benzene. We must have a double bond, then a single bond, and a double bond here. But the experimental evidence suggests that the benzene is completely a symmetrical system. So it's a 6-membered ring in which all bond lengths are same and are equal to 1.39 armstrong. So in general, a single bond length is 1.47 armstrong, while a double bond length is 1.34 armstrong. So you can see that in case of benzene, the carbon-carbon bond is longer than double bond and shorter than a single bond. So this bond length of carbon-carbon bond is intermediate between a true single bond and a true double bond. So we say that in benzene ring, the bonds between carbon and carbon, they are not true single or true double bond, but instead all of the bonds are same and they are intermediate between single and double bonds. So benzene is a symmetrical system. You can see here, so benzene is a symmetrical system, and this symmetry is maintained by the sigma framework, which is forming the single bond system, and also by the pi electrons. So these pi electrons are forming a cloud above and below the benzene ring. So the sigma bond as well as the pi electrons, they are forming the symmetrical system of the benzene ring, right? So benzene ring has electronic density above and below the sigma framework. So benzene is an electronically rich system, right? And it has delocalized electrons, which is responsible for the extraordinary stability. And that's for the same reason benzene does not undergo addition reaction, because if benzene undergo addition reaction, the pi electrons will be lost. If pi electrons are lost, delocalization will vanish and the stability will be lost, but benzene wants to remain stable. Therefore, it does not want its pi electron to be lost, so it does not allow addition reaction, right? So whenever you are asked why benzene does not undergo addition reaction, because benzene is a stable molecule because of its delocalization of pi electrons. So if addition reactions occur, pi electrons will be lost, so delocalization will be lost and the stability will be lost too. So now let's consider the heat of hydrogenation, right? So whenever we have to consider the stability of a system, the simplest way is to see the heat of hydrogenation, right? So we'll compare the heat of hydrogenation of benzene with that of 1,3-cyclohexadiene and cyclohexene. So here we are imagining that benzene is cyclohexatriene, right? So in this calculations of heat of hydrogenation, we will be assuming that the structure of benzene is same as the structure of cyclohexatriene, right? So we'll compare the heat of hydrogenation of this cyclohexatriene with that of 1,3-cyclohexadiene and cyclohexene. So why we are choosing cyclohexadiene or cyclohexene? Because all of these molecules, when they undergo the hydrogenation process, so all of them will form the same product, that is cyclohexene, right? So let's consider the hydrogenation of cyclohexene. So cyclohexene has one double bond. So when hydrogen adds to this double bond, then an amount of 28.6 kilocalorie per mole of energy is released, right? So this is the energy which is released when we carry out hydrogenation of a double bond. But in case if a molecule has two double bonds which are conjugated, then in that case this heat energy evolved should be almost double. So this energy is almost double, but this amount is small has reduced to some extent. So there is a slight decrease in heat of hydrogenation of a system which is cyclohexadiene in case if the double bonds are conjugated. Why the decrease in energy when we are carrying out the hydrogenation of a conjugated system is because of the resonance stabilization, because system is conjugated, so it must have resonance, right? So because of resonance, so the heat of hydrogenation has reduced. You can say 2.3 kilocalories per mole has reduced, so it must be double of this value, but it's almost double, but it has a deficiency of 2.3 kilocalories per mole, right? So the deficiency is explained by the resonance stabilization of the conjugated diene. So now we'll consider the hydrogenation of cyclohexatriene, right? So we are assuming that benzene is just like cyclohexatriene, so it has 3 double bonds. It means the heat of hydrogenation should be almost 3 times, right? So let's do the calculations. So for hydrogenation of 1 double bond, an energy of minus 28.6 is released. So since there we are having 3 double bonds, so multiply it by 3 plus. So in case if a system is conjugated, then with increase in conjugation, so an extra of 2.3 kilocalories per mole of energy is to be added. So since we are having 3 double bonds which are in conjugation, so we'll multiply 2.3 with 3, right? So the sum becomes 78.9 kilocalories per mole. It means that if we have to carry out the hydrogenation of cyclohexatriene, then in that case this much amount of energy must be released. So if benzene is actually cyclohexatriene, then the heat of hydrogenation of benzene should be this as well. So let's consider the system, right? So we have cyclohexene. In cyclohexene we have a double bond, and you know that in cyclohexene the heat of hydrogenation is 28.6 here. When we are having 2 double bonds which are in conjugation, then we have this much amount of energy, which is almost double to that of single bond. In case if we have 3 double bonds which are in conjugation, then this is almost 3 times the value of the cyclohexene here. But when we carry out the heat of hydrogenation of benzene, this value is very reduced. So benzene, actually the heat of hydrogenation for benzene is minus 49.3, right? So this is far too low. This is even lower than the hydrogenation of 2 double bonds. So what does that mean? So this energy difference between the cyclohexatriene and benzene is almost minus 29.6 kilocalories per mole. We say that benzene is actually stable than 135 cyclohexadiene triene by a factor of minus 9.6 kilocalories per mole, right? So this energy difference between the cyclohexatriene and benzene, this is known as the resonance energy of benzene, right? So resonance energy of benzene shows that benzene is almost 30 kilocalories per mole more stable as compared to 135 cyclohexatriene. It also suggests that benzene is not 135 cyclohexatriene. So benzene is not just a simple double bond system which are in conjugation with each other, right? So according to this experimental data, we see that the heat of hydrogenation of benzene is minus 49.3 kilocalories per mole, which is much less than the predicted value of minus 78.9 kilocalories per mole. This value indicates that benzene is very stable than the conjugated cyclotriene system. So this energy difference of the benzene and cyclohexatriene is known as resonance energy. It's also known as delocalization energy, or it's also known as aromatic stabilization, or it is simply known as the aromaticity, right? So in the start of lecture we saw that aromaticity was actually associated with smell, but now whenever you read the term of aromatic or aromaticity, always remember it is actually referring to the stability of a system because of delocalization of the bioelectrons, right? So here when we are saying the aromaticity or aromatic stabilization, we are mentioning or we are referring to the stabilization because of delocalization of the bioelectrons. Right, the structure of the benzene is a regular hexagon. So hexagon means a six-membered ring, and when we say regular hexagon, so regular geometry is a geometry in which all bond lengths and all bond angles are same. So the benzene has a six-membered ring in which all bond angles and all bond lengths are the same. So all carbons are sp2 hybridized. The carbon-carbon bond length is between a single and a double bond, so it's not pure single bond and it's not pure double bond. Further, we have also seen that the pi electrons of which are residing in the p orbital, they form a cloud above and below the plane of the ring, right? So since benzene is conjugated and it has delocalization, so benzene can be represented by different contributing structures of cyclohexatriene, but cyclohexatriene is not actual benzene, so it's just a way to represent the structure of a benzene, right? And also we have seen that hydrogenation of the benzene releases about 30 kilocalories per mole of energy, which is less than that of if it were cyclohexatriene. So this difference in energy of hydrogenation between benzene and cyclohexatriene, this is known as the resonance energy of benzene. So that's all for today's lecture. I hope you have understood it well. Thank you.